started. So welcome to the YEA Physics lecture series. Today I'll be reviewing some of the content on the AP Physics C Mechanics exam. Okay, so our first topic to review is vectors. So as a quick review, vectors are quantities with both magnitude and direction, as opposed to scalars. So scalars just have a magnitude, but no direction. And you can see here, these are just some common notations for vectors. All right. And let's talk also about components. So components are just like we can decompose some vectors into, for example, you might have an X component or a Y component, and you can decompose any vector into a sum of its X component and Y component. And so this will sometimes make problems easier. All right. And I did mention adding vectors just as a review. To add vectors, it's simply you just take the tail of one of them and put it at the tip of the other. And yeah, you get your added vector. In terms of components, you can see it's as easy as just adding each individual component of the vector. And multiplying vectors by a scalar is also quite easy. It's equivalent to scaling it by some certain factor, and if the factor is negative, it'll also reverse the direction. And in terms of components, it's also quite easy. You just multiply each component by whatever value. All right, now let's talk a bit about dot products and cross products. So these we might have to review a bit more. So a dot product, these are both for two vector quantities, right? So let's say we have a dot product of these two vectors. In terms of the components, I wrote the formula on the slide. That's actually the formula for a two-dimensional vector, but for three-dimensional vectors, it's very similar. It's just like, I don't know,
Okay.
AX, AY, AZ dot BX, BY, BZ equals, you just take the first term of the first vector multiplied by the first term of the second vector, and then do the same thing for the second term, and so on. And you add them all up. And geometrically, what this is equivalent to is if you have your two vectors, the first vector is length A, the second vector is length B, and there's an angle theta in between them. The quantity A dot B will be equal to the length of A times the length of B times the cosine of the angle between them. Okay, now for cross products, I also wrote down the equation in terms of components on the slide there. But if you want like a geometric interpretation again, the cross product of two vectors, so we have A and B. So A cross B is going to be a vector and it has magnitude of AB sine theta, where theta is the angle between them. And the direction is determined by the right hand rule. So I guess how to explain this, if you go from like if you have to go clockwise to get to B, then it will be downwards. But if you do like, if this was A and this was B, and you're going counterclockwise, then it would be upwards. But anyways, the direction is basically if you have two vectors in 2D, the direction will be either into the page or out of the page, and it'll be determined by the right-hand rule. The right-hand rule is kind of hard to draw, so I don't know, if you don't know the right-hand rule, I would recommend looking up some pictures online. Okay. And as I've already been mentioning, vectors have magnitudes, and the magnitude is simply the length of the vector. And if we have the components of the vector, we can easily compute the magnitude by just using the Pythagorean theorem. So square root of x component squared plus y component squared. And direction, vectors also have a direction, and you can compute that using arctangent. So if you can see here that this side is 3 and this side is 2, then you can compute this angle sort of as arctangent 3/2. Okay. Now let's go on to a bit of kinematics. All right, so first some definitions to review. Displacement is a vector and it's based off of an object's change in position. So if we have an object that starts right here, say, and it moves somewhere, it moves there, the displacement is just a vector from its starting point to its finishing point. That's the displacement. Now the distance is a bit different. The distance, it's just how far the object moves, and it depends on the path. So this path here, in this case, the distance will be the length of the path. We also have velocity, which will be the rate of change of displacement. So it's a vector. It's basically which direction are you going? And it's the derivative of the position. And I guess if you don't know calculus, then just think of it as the difference in position divided by the difference in time. And yeah. Okay. And The speed is very similar, but it's the derivative of distance. So I think this will work out to be the speed is often just going to end up being the magnitude of the velocity, because distance is kind of the magnitude of displacement. And lastly, acceleration is the rate of change of velocity. So it's the derivative of velocity. So if we have velocity is a change in x over a change in t, then acceleration would be a change in v over a change in t. Yeah. Okay. So let's do a quick practice problem here. I've launched a poll. Just so I'll give you guys maybe on the actual test, you should be doing these questions in roughly a minute per question max. So yeah, please do the poll. It's very cool. And I'll end it after roughly a minute. All right, it's been roughly a minute since I've stopped talking. So let's end the poll and see, look at what happened. So yes, a lot of people answered D, and I am pretty sure D is the correct answer. So that's pretty good. Yeah. So how do we do this question? It's basically just based on the definitions of speed or velocity and distance and displacement that I just went over. So displacement, okay, so the distance is the total length of the path. That's just 400, right? And the displacement, as I said earlier, it's a vector from the starting point to the ending point. And so in this question, he starts and ends at the same point, which means that the displacement is actually zero in this case. Now, what about average speed? Average speed would be the distance divided by time, so that's 40. And average velocity would be the displacement divided by time, so that would be 0. Okay. Um, Now let's go on to the next question. This question isn't multiple choice, but feel free to send me your answers in the chat or something. Okay, let's start talking about this question. So, yeah, so we just have an object here, and we know its acceleration as a function of time. A, oops, A of t, we know is equal to alpha t plus beta. So the question just asks us to find the velocity and position. So to do this, well, we know that A is acceleration is the derivative of velocity, right? Which means to go the other way, we would just take the integral. So velocity is the integral of position. And so if we integrate once, we'll get 1/2 alpha t squared plus beta t. And it starts at rest, so the constant of integration is 0. And then if we integrate again, we should get x of t equals 1/6 alpha t cubed plus 1/2 beta t squared. And again, the constant of integration is 0, so these should be our answers. And okay, so now let's talk about kinematic equations. So we know the equations A equals dv dt and v equals dx dt. These are just the definitions. But if we assume that there's constant acceleration, we can also derive some other equations. So these three equations, these three on the bottom here, I think they're given to you on the formula sheet. But anyways, these are equations you can use under constant acceleration. So that's very important. If the acceleration is not constant, you can't use these. But anyways, these are equations that you can quickly plug in stuff to find answers. So let's do a few more example questions. All right. It's been a bit more than a minute since I've launched the poll. And just a quick comment, this is roughly the pace that you would need to do multiple choice questions on the AP exam, because I'm pretty sure the format is 45 minutes for 35 questions. So yeah, you should be going at just a bit more than a minute for per question. Of course, some questions are easier, so maybe you can do those quicker and get more time for the harder questions, but generally just like roughly a minute per question is a good pace to go. All right. So I'm going to end the poll here and let's share the results. So a lot of people chose C, which is good because C is the correct answer here. So what is going on? We have an object that we have an object that's thrown upwards and its initial speed is 8 meters per second. Okay. So now it takes 3 seconds to strike the ground. So it's thrown upwards, it falls a bit, and now it strikes the ground 3 seconds later. So we want to find this height. And how will we do that? Well, we can use one of our kinematic equations. So from the previous slide, which equation do you think would be the most helpful? Yeah, so we know the velocity, we know the initial velocity, we know acceleration, and we know time. So we can use equation 2 to immediately calculate our answer. So what equation 2 gives us is that x is going to be our initial x, so h, oh wait, so our final x is going to be 0. So if I want to write it this way, I should probably say 0. That's our final position is equal to our initial position, which is h, plus our initial velocity, which is 8 meters per second, and t is 3 seconds if we go back to the problem. Yeah, t is 3 seconds. And then plus 1/2 at squared. And since our object's under free fall, we're just going to use -10 for our acceleration. And t squared will be 3 squared. And if you do the quick maths, you will get that h is 21 meters. Right, so that's our answer. Cool. Now let's go on. So again, this is not multiple choice, but I'll give you roughly a minute. This is a multiple choice level difficulty problem. All right, yeah, it's been like a minute, so hopefully you're done. And so how will we do this question? We know that the rock is here, it's dropped 100 meters, and we know that its acceleration is 10 meters per second squared downwards. And we want to find its final velocity. So if we go back to our list, which equation here do you think will be the most useful? Three, yeah. Equation 3 is definitely the most useful in this case because, well, because it just gives us the answer immediately. We'll get that v squared equals the initial velocity squared, well, the initial velocity is 0, plus 2 times acceleration, which is 10, times the distance, which is 100. And so this is 2000, which means that we'll get v squared is 2000. And taking the square root, our answer should be approximately 45 meters per second. Okay. Um, if there are any questions, feel free to ask. Or if you feel like I'm going too fast or too slow, of course, also feel free to let me know. But if there are no questions, let's go on to the next section, which is kinematics in 2D. So in 2 dimensions, it's actually very similar to the 1-dimensional case, except we'll have to solve a kinematics problem in each dimension. So we'll have to solve the equations in the x dimension, but we'll also need to solve the equations in the y dimension if it's 2 dimensions. So yeah, we can write down separate equations for each dimension, and the equations that we learned for 1 dimension still apply for each one of our dimensions in this case. So now let's
Could I
go
have more
straight
drink
to
now, please?
another example.
I'm just moving this.
And let's relaunch the poll. Okay, Yeah, it has been roughly a minute, but this is definitely a more complicated problem. So it would be all right to spend slightly more time on problems like this. So yeah, I'll give you maybe another 30 seconds and then I'll start talking about the question. Okay, so that is time. And I will end the poll now and start talking about this question. So this time we had a more interesting distribution. Two people chose A, which is, I mean, three people chose A, which is good because I think A is the correct answer here. Two people chose D, and one person chose F. So a pro tip here, please don't choose F on the actual exam because it's just not going to be the correct answer. And you should always answer all of the questions, even if it's just a complete guess. Like even if you haven't read the question, of course, it's still beneficial to put an answer because there's no penalty for wrong answers. And there's always a chance that you guess it correct. So now let's do this question. We have a projectile and it's launched at some angle theta, but we don't know what theta is. And there's some sort of wall here. The wall has height h and it's a distance d away from the launch point. And so we want the projectile to hit exactly the top of this wall. So how will we do this? Well, we can start by writing out the kinematic equations for both directions. So what happens in the x direction? Well, the x distance it travels is just going to be the initial x velocity. So v times cosine theta. That's the x component of the velocity. And in this case, there is no acceleration in the x direction because, well, there's no force acting on it. In these projectile problems, there's almost always no acceleration in the x direction. So it's just velocity times the time. Now, in the y direction, there is an acceleration. It's g downwards. So we'll have the initial y velocity and then minus 1/2 g t squared. Okay, so now what happens when the projectile hits the wall? Well, we know that the wall is a distance d away, So we have to have D is equal to V cosine theta T once the projectile hits the wall. So from here, we can solve for T. T equals D over V cosine theta. And now we can plug this into our equation for Y. In this case, Y has to be equal to H. So we'll get that H equals V sine theta T. T is D over V cosine theta. And minus 1/2 GT squared, or D over V cosine theta squared. And this will give us, after we simplify, we'll get D tan theta minus 1/2 GD squared over V squared cosine squared theta. So that is our answer. Okay. So now let's go on to Newton's laws. So just as a review of Newton's laws, Newton had three major laws, which were the first law: an object will continue on in its motion unless it's acted on by a net force. And that's also sort of a special case of the second law, which says that the force on the mass will cause an acceleration. And so if there's no acceleration, or if there's no force, there's no acceleration. And Newton's second law, of course, it's directly proportional to the acceleration, and the force is equal to the mass times the acceleration. And Newton's third law is just every force causes an equal and opposite reaction force. Hopefully you should know this stuff already. And now let's list out some common forces. So we have weight, or gravitational force. And on the surface of the Earth, it's just mg downwards. So if we have a box of mass m, there will be a force mg downwards. Also, quick side note, this sort of diagram is a force diagram, as you should probably know. It's basically just a box and arrows on it for all of your forces. So yeah, you might be asked to draw one of these force diagrams on the test. Just know that you just have to draw arrows for all the forces. And secondly, we have normal force, which is kind of like whatever is necessary to support the object. So if we have the box is sitting on a table, then the table will provide some sort of normal force. And in this case, it will be mg upwards. And it has to be mg because otherwise the box will either fly off into space or sink through the table. So either of these cases don't really happen. So we know that the normal force has to be equal to mg in order to balance out the gravitational force. Now we have friction. So friction is divided into two cases. There's static and kinetic friction. Static friction is friction for an object at rest. So let's say I pull on this box with some force F. If I don't pull hard enough, there's going to be a static friction force that basically prevents the box from moving. And as long as my force is less than the mu s times Fn, the friction force will continue to increase to match my force. However, let's say I start applying a really big force and now the box starts moving. Well, now the friction force becomes just a constant and it's equal to mu k times Fn. So those are the two types of friction. And there's also spring force, which is just the force of a spring. So if we have this our mass here, and it's attached to a spring, and the spring is stretched a distance x, then wait, no, this is probably not the best way to draw it. So if the spring is stretched a distance x, then the force will be kx, and it's in a direction opposite to the direction the spring was stretched. So that's spring force. And a side note here is circular motion. So if an object's in circular motion, well, it is what it sounds like. It's just moving in a circle, and it's uniform circular motion if the speed remains constant. Okay, so notice that the speed here is constant, but the velocity is not, because the velocity is constantly changing direction. And this means that there needs to be an acceleration. So if our object here is moving in a circle, in order to keep moving in a circle, it must be constantly accelerating radially inwards, which just means towards the center of the circle. It has to be accelerating, and the magnitude of the acceleration has to be equal to v squared over r, where this is r, this is its velocity. And this is known as the centripetal acceleration. So now let's do a few practice problems, and I will reopen up our poll. Okay, yeah, so it's roughly 1 minute. You should be done by now. And it looks like most people answered D, which is indeed the correct answer. And so what's the idea behind this question? Well, we have an elevator here, So a person is in the elevator, and let's say the person's standing on a bathroom scale. So the bathroom scale, what it really does is measure how much normal force it applies to this person. So normally, if the person's not in the elevator, he's just standing on the bathroom scale, there's gonna be his weight downwards and his normal force upwards, but the normal force will be equal to his weight because he's at rest. So the net force has to be equal to 0. However, now in the case of the elevator, well, the elevator is accelerating upwards at 10 meters per second. And the person's inside the elevator. So the person is also accelerating upwards at 10 meters per second, which means by Newton's second law, the net force on the person must be equal to ma, or m times 10 meters per second squared. And if we're using g equals 10 meters per second squared, then this does happen to equal to mg. And so that's the net force. So once we draw our forces, there's going to be mg downwards, and there has to be a normal force that's twice of his weight in order to balance out the gravity and make the net force equal to his weight. Okay. So that's how we do that problem. Let's go on to the next problem. Okay, yeah, let's start doing this problem. This is kind of a classic inclined plane problem. And what we do here is an inclined plane at an angle of theta, and we have a mass m. So let's think about what forces first, what like individual forces it experiences. Well, it's got to experience two forces here, which are gravity and normal force. And there aren't any other forces here because there's no friction. The problem says the plane is frictionless. And yeah, so it's just gravity and normal force. And so to find the net force, we have to just sum these two forces. Okay, so how are we going to sum these two forces? First of all, we should find what the normal force is. And it turns out the normal force is equal to mg cosine theta. Now, why is this? Well, if we look at it in terms of the components of the gravitational force, well, the gravitational force has a component here that's mg cosine theta, and a component here that's mg sine theta, because this angle here is theta. That's just true by geometry. Yeah. So we split gravity into components. And now, well, what's going on here? The block cannot accelerate into the plane, right? And it can't accelerate out of the plane. So the acceleration perpendicular to the plane must be 0. And that's why our normal force has to be equal to mg cosine theta, because that will balance out the perpendicular component of our gravity. So what's left over is actually just this horizontal component here. And so that's our answer. Mg sine theta is the net force, and it goes down the plane. Okay. Cool. Now let's move on to another problem. So, yeah. I'll let you think about this problem for roughly a minute. We have to go a bit quickly because we are a bit low on time. Yeah, okay, it's been about a minute. So let's start doing this problem. And so to do this problem, first, we should draw a force diagram. So we have a pulley, a big mass M. So the two forces here are gravity and tension from the string. And it's the same thing on the other side. There's going to be gravity and tension from the string. And the key observation here is that if this is an ideal massless string, then the tension has to be the same throughout the string. So from there, we can get two equations, which will be the F equals ma equations for both masses. So for the first mass, what's the force on it? Well, it's just mg minus our tension, and it has to be equal to ma. And the second mass, the force on it is the tension minus mg, so it has to be equal to ma. And now to solve this for A, all we have to do is add them up. Mg minus mg equals ma plus ma, and we'll get that the acceleration is equal to m minus m over m plus m times g. So that's our answer. Okay. Now let's move on to our next section, which is about work, energy, and power. So let's start with our definitions. First of all, work is a force applied over distance, so integral F dot dr. And for a non-calculus version of this, I guess this will just be constant force. So if the force is constant, then the work is just the force dot the displacement. So this is the dot product. So we can also write it as the force times the displacement times cosine theta, where theta is the angle between them. Okay. And we also have here the kinetic energy, which is given by 1/2 mv squared. And the reason why it's 1/2 mv squared is because that way, if we do some work on an object, the work will be equal to its change in kinetic energy. And we have work, we have kinetic energy, we also have potential energy. So this is sort of this is something we just add on to energy, so we don't have to keep track of work done by, for example, if we don't want to keep track of work done by gravity, we can just say we can just add on its potential energy. So in this case, it will be mgh, because if we have a block that's mg, that's mass m, we'll have gravity that's mg downwards. And if we try to pull it up a distance h, then we'll have to apply a force that's equal to mg. And so the work is the force times the distance, which is mgh. And so we are sort of storing mgh energy, which will be released later on if we drop the block. If we drop the block, then the energy will be released as kinetic energy. And we knew that energy is going to be integral F dr, right? And similarly, if we take the derivative, we'll get F is equal to negative du dr, where U is the potential energy. This is because the way we define potential energy, U is actually negative integral F dr. So that's where the negative sign comes from. It's negative because we're like taking away energy because we're like storing it inside of our potential energy stuff. So yeah, this is sometimes useful if you get like maybe sometimes if you get a potential energy graph, you can see maybe the slope here is 0, so you'll know this point's at equilibrium. Or if they give you a potential energy function, like, I don't know, U equals square root X, then you'll know what the force is as a function of X. Oh, yes, I did forget to talk about spring potential energy. So spring potential energy, you can get that by integrating negative kx dx because this is the spring force and this is 1/2 kx squared. That's where it comes from. And yeah, this is just another form of potential energy. Okay, and conservation of energy, you should probably all be somewhat familiar with. It just states that the total energy, so kinetic plus potential, it's going to remain constant. So your initial energy, even after a bunch of stuff happens, the final energy should be the same as that initial energy. And this is quite useful when you're solving problems. Another definition here. Oh, there's a slight typo in the slide. Hold up. Yeah, power is FV, not FR. Yeah, so power is defined as the rate of change of energy, so just dE dt. And another form of power that shows up sometimes is power is the force times the velocity. So yeah, just know that power is a change in energy divided by a change in time. Okay, let's do some more examples. Oops. And since we are a bit low on time, I'll just give you the slightly more than 1 minute per question that you'll get on the real exam. Okay, that was around a minute. So you should be roughly done by now. So 4 people answered B, which is nice because the answer is B. And this problem's actually pretty straightforward. This is just a direct application of just your block. A force is acting on it. This angle is 60 degrees. So then we can use our equation work equals force times distance times cosine theta. Our force is 100. The distance is 1 and cosine 60 is half. So the answer here is 50 joules. Okay. Yeah, let's move on to the next one. So again, 1 minute here should be enough to do the problem. Okay, it's been roughly a minute. Uh, hopefully you're done by now. Yeah, this is just so you can basically just apply conservation of energy. So right here, the block is at a height h, and at the bottom, the block is at a height 0. So if what you would do here is the initial energy is equal to the final energy. And initially, there's no kinetic energy. So if we do kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Well, initially, there's no kinetic energy, and we have mgh gravitational potential energy. Now at the end, it's kinetic energy. That's what we want to find, 1/2 mv squared. And it has no potential energy because it's at height 0. So now all we have to do is solve this equation and we'll get v equals root 2 gh. Okay, now let's go on to the next question. Again, I'll give you about a minute to do this, and then we can discuss. Oh wait, I should launch a poll because, yeah, oh, I'm going to relaunch the poll because this is a multiple choice question. All right, 1 minute is up. You should be pretty much done by now. So I'm going to stop my poll. And seems like most people chose E, which is the correct answer here. So for this question, all we have to do is remember the definition of power. Power is energy divided by time. So in this case, we know the power and we can find the energy. So the time it takes is just the energy divided by power. And in our case, energy is mgh over our power. And if you plug in the numbers, m is 0.1, g is 10, h is 2, power is 0.5, and this will give us 4 seconds. So that's our answer. Now let's talk a bit about momentum. So what is momentum? It's defined as the product of mass and velocity. So since it's the product of a scalar and a vector, it is a vector. And we can use it actually because acceleration is the derivative of mass. And force is mass times acceleration. That means that force is the derivative of momentum. And we can use this if we integrate F equals dp dt. What we'll get is that something known as impulse. So the integral of F dt will give us the change in momentum. And this is known as impulse. And conservation of momentum is another key property. And basically what it says is if you have a system that's just an isolated system, momentum will be conserved. And this is a result of Newton's third law and also the impulse momentum theory. And conservation of momentum is very important for problems involving collisions because, well, momentum is conserved there. So yeah, it's just useful to, I guess you get another equation. And also you should know that momentum is a vector. And so what this means is that if you have a two-dimensional collision, you need to make sure that momentum, the x component of momentum is the same, but also the y component of momentum is the same. So each component is conserved. And collisions, a bit more terminology here. Elastic collisions are collisions that conserve kinetic energy, and inelastic collisions are collisions that don't conserve kinetic energy. So, and most of the time you'll be dealing with completely inelastic collisions, which are just collisions that where the objects stick together. And they're called completely inelastic because I'm pretty sure that's the scenario that loses the maximum amount of kinetic energy. That's just a fun fact. Okay. And also something that might be useful to know is stuff about the center of mass. So the center of mass is literally just the center, right? It's calculated as a weighted average. So I guess the center, the average position of everything. And similarly, the center of mass might move. So it can also have a velocity and it can have an acceleration. And this acceleration is interesting because if we differentiate that center of mass velocity equation once more, we'll get that the net force, or the sum of all the forces acting on the particles, is equal to the total mass times the acceleration of the center of mass, which basically means that in some ways you can just consider the group of particles to be a single particle at its center of mass. Okay, so let's do another example problem here. All right, it's been about a minute. This problem's relatively straightforward, so hopefully you're done by now. I'm going to end the poll. And the answer is indeed E. Someone chose F. I'm not sure if they misclicked or yeah, okay. I don't know yet. As I said earlier, on the actual exam, please don't choose F. Please always choose an answer, even if you don't know what it is. Um, so yeah, so how will we do this problem? Well, first the impulse. Let's recall the definition of impulse. Impulse J is equal to the change in momentum. In this case, well, the mass is constant, so this is just mass times the change in velocity. So the mass is 5 kilograms. The change in velocity is 3 meters per second. So this is 15 kilogram meters per second. So that's the first part. And time averaged force, well, there's two ways. You can just like calculate the acceleration and multiply it by the mass. Or since you already have the impulse, you might as well just use force equals impulse divided by time. And so that will give you 5 newtons. So the answer is E. Okay. So if everyone's good with that, now let's move on to the next question. All right. Yeah, it's been a minute. So I'll close the poll. And this time everyone got it correct. So yay. I'll just quickly explain. Yeah, if there's no net external force, then momentum is always conserved. So B is wrong and D is wrong. And if there's some kinetic energy that's lost, it's also not elastic. So the correct answer would be C. Okay, let's go on to the next problem. Okay, it's been a minute. So hopefully y'all have finished by now. The answer is B. So how do we do this question? It's just conservation of momentum. So we have a 1 kilogram mass that's going to the right at 10 meters per second. And it collides perfectly inelastically with a 4 kilogram mass. So after the collision, this is basically just equivalent to a 5 kilogram mass that's moving at some velocity v. Okay, but we have to have conservation of momentum. So what's the initial momentum? Well, it's just 1 kilogram times 10 meters per second. And the 4 kilogram mass doesn't have momentum. So this is just the total momentum is 10 kilogram meters per second. And after the collision, the momentum is just 5 kilograms times v. But this has to be equal to the initial momentum by conservation of momentum. So this is 10 kilogram meters per second, which means that v must be equal to 2 meters per second. Okay. Now let's go on to talking about rotational motion. So there's a lot of content here. We say this is a formal definition of whether it is an object rotating around a point. So the main idea here is that the velocity is going to be omega times r up to some constant. And we can think of this object also as rotating through an angle. So maybe we have, this is the initial state of the object. And now it's like this. So it's rotated an angle theta. And then our angular velocity is just going to be d theta dt. And this is measured in radians per second, of course. And similarly, we can also define angular acceleration alpha, which is just d omega dt. And if you notice, this is like very similar to the definitions of velocity and linear acceleration. So we can in fact use basically the same equations. It's just that whenever you see x, you have to replace it with theta. Whenever you see velocity, now it's angular velocity, and then acceleration is now angular acceleration. And like their translational counterparts, these are only valid under constant angular acceleration. So now let's talk about torque. So torque is defined as r cross f. So it is a vector. Its direction kind of determines whether it's clockwise or counterclockwise. And to see that stuff, it depends on the right-hand rule. And why is torque useful? Well, first of all, let's define a rotational inertia. And it's defined as mr squared for a single mass. So if we have like some axis here and a mass that's rotating around, if this is r, then the moment of inertia is mr squared. If we have a collection of masses, we just add up each mr squared. And for a continuous distribution, yeah, it's just the integral form of adding everything up. All right. So now we can get to why. Oh, first of all, some formulas. So common ones. Uniform rod around its center. So like this. Cylinder around its axis. So sort of like this. And then sphere, hollow sphere and uniform sphere. Those are also common formulas. I'm not sure whether the College Board makes you memorize these or not, but regardless, they're good to know. And if it's anything more complicated than this, they'll probably tell you they'll probably just give you the moment of inertia. And if they don't, there's also an interesting theorem that you should know. So the parallel axis theorem will help you calculate the moment of inertia. So let's say you know stick around center, right? You know stick around center. But what if they ask you for stick around one of its ends? Well, if we know stick around its center, we can use the parallel axis theorem. So we'll get 1/12 ml squared plus md squared. Well, d is L over 2. D is this distance from the center of mass to the new axis. And if you add this up, you'll get 1/3 ml squared. And that is indeed the correct formula for stick around its end. Okay. Now we can finally get to Newton's second law for rotation, which is torque equals I alpha. So this is very similar to F equals ma, because we've already established that alpha is angular acceleration. It's basically the same as normal acceleration, but for angles, right? So now all we have to do is just say torque. So translational force is going to become torque. And translational mass or translational inertia, which is just the mass, is going to become our rotational inertia. And so now we can use all of our same formulas again. And just a word of caution, make sure that you're paying attention to what pivot or what rotation axis everything is around, because torque does depend on which axis you're computing it around. So yes, this is kind of tricky sometimes. And another interesting formula is kinetic energy. This is pretty easy to remember because kinetic energy of a moving object is 1/2 mv squared. And if you make these substitutions, well, m becomes I, becomes omega, and you get the equation for rotational kinetic energy. And as for this warning, yeah, this is kind of important because let's say you have a ball that's both rolling, but it's also moving at the same time. So if it's rotating and moving, you have to add these two actually. So this will be your actual kinetic energy. Okay. So for work and power, similar things. So power, torque, omega, that's basically the same as force times velocity for the translational case. Work is torque times theta, which is like also kind of expected because that's like force times distance, but for rotation. So yeah. And angular momentum. Oh, so this is important. Angular momentum is defined as mr cross v. So that's for a single mass. That's a single mass. So around this axis, if we have r and a mass that's traveling at v, then this is our angular momentum. And just like F equals dp dt, we have torque equals dl dt. So yeah, you can also have stuff like angular impulse or whatever. And if you have like a weirdly shaped object, its angular momentum is I omega. That's sort of just, that's the equivalent of P equals mv, I guess. Yeah. So now conservation of angular momentum. Angular momentum is also conserved whenever there's no external torque. And this is also useful if you're colliding with things that are weirdly shaped. And yeah, so sometimes you'll see collision problems. Or more often than not, you'll see like, well, just in general, there's also the famous ice skater problem. So like an ice skater pulls in their arms and decreases their moment of inertia. But because of conservation of angular momentum, before they have they have the same angular momentum, so that means their omega will increase. So now let's briefly talk about statics. Whenever you see a problem, say, whenever you see like the setup's gonna stay the same in the problem. So like if you have two people balancing on a seesaw, or if you have like a ladder leaning against the wall and the ladder doesn't move, then these are all problems where you're going to want to let the net force and net torque be equal to 0, because these will give you valuable equations that you can use. And also another side note, rolling without slipping, you can like say, it's basically when the object is rolling like this, but the point of contact here has 0 instantaneous velocity. So how does this work? Well, if it's rolling with omega angular velocity, the speed of this point relative to the center is going to be r omega. But if the center is moving at a speed r omega, that means that this point here is stationary relative to the ground. And so that's how it rolls without slipping. And so whenever you have rolling without slipping, you'll have V equals R omega. And by extension, this also means that A equals R alpha. And this also means that delta X equals R theta. So yeah, good to know if you see something rolling without slipping. And ooh, this is quite a long example. I think I'll just explain how to do this because we're a bit low on time. So we have a sphere rolling down an inclined plane. So there's a couple of things going on. First of all, it's rolling without slipping. And there has to be gravity, normal force, and there also has to be friction force. Now, why is this? Because it's accelerating, right? So its velocity has to keep increasing. But if V equals R omega, that means, well, omega has to keep increasing. So there has to be some sort of torque. And the only thing that can apply that torque is friction, because friction acts at the edge of the sphere, not at the center, unlike gravity or normal force. So let's consider the contact point as our pivot then. So what's the torque? Well, the torque is the only force that provides a torque actually would be gravity in this case. Because if we draw it out, this is the contact point. Gravity will go this way in this frame, normal force this way, and friction acts at the contact point. So if this is our pivot, then the only thing applying a torque will be gravity. We can also solve it with the center of mass as our pivot. In that case, the only thing providing torque will be friction. So this is important that you keep track of where your pivot is. So let's just assume we decided to go with the contact point. Then the torque will be Fg times r times sine theta, right? because torque is R cross F. So this will just be mgr sine theta. And now we get some alpha. So alpha is torque over I. Well, what is I then? To find I, notice here I is the moment of inertia around the contact point. So we have to use the parallel axis theorem. It'll be the 2/5 mr squared plus an additional mr squared because the contact point is a distance r away from the center. And this will all simplify to, 5g sine theta divided by 7r. So now all that's left to do is to find the acceleration of the center of mass. And this acceleration has to be equal to r alpha, which is equal to 5g sine theta over 7. Okay, and that's our answer. Now, let's go on to our next example. I'll open the poll again. And this should be a pretty straightforward problem again. I'll give you 45 seconds because we're short on time. Okay, it has been almost a minute, so let's just end poll. So this is a bit interesting. One person answered B, 2 people answered D. So the correct answer is actually D. And the reason why is, remember, so V is equal to R omega, but this omega has to be in radians per second. So our 10 revolutions per second, well, 1 revolution is equal to 2 pi radians. So this is actually 20 pi radians per second. So then from there, we can get that it's roughly 2 pi meters per second, or roughly 6.3. Okay, so yeah, watch out for revolutions versus radians. Just watch out for units in general, because they might try to trick you with units. Now let's go on to the second example for this section. Okay. So. Yeah, let's end the poll. It's been roughly a minute. And yeah, so I think if I remember correctly, the answer was actually C. So let's do this question. To do this question, we simply need to use one of our kinematic equations. So in this case, omega final squared equals omega initial squared plus 2 alpha theta. So then we can just solve for theta. Theta is omega final squared minus omega initial squared to alpha. And this will be 5 squared minus 2 squared over 6, which is 3.5. So that is our answer. All right. And let's go on to now the next one. I'll relaunch the poll. Okay, yeah, it's been like a minute, so hopefully you're at least close to being done. I'll just end the poll here. So half of you chose A, half of you chose B. The answer is A, and whoever chose B probably just forgot to divide the length by 2, because what's going on here is that the entire seesaw has length 4, but this length is 2 meters and this length is 2 meters. So if we have Alice on one end that applies 500 newtons of weight and Bob on this end 600 newtons, the net torque is going to be 600 newtons times 2 meters minus 500 newtons times 2 meters, because they're going in opposite directions, and we get our answer of 200 kilogram meters squared per second squared. All right. And I'm going quite quickly here because we have another 2 sections to go through. So let's go through gravitation. Yeah, so this is Newton's law of gravitation. So it's proportional to both masses and it's inversely proportional to the square of the radius. So you should hopefully know that by now. And we have Kepler's law. So the first law and the second law are a bit less important on the exam, but what we want to focus on is the third law here, because that gives us a very useful formula, which relates the period of an orbit to the length of its semi-major axis. So yeah, period is proportional to the semi-major axis to the 2/3 power. So that's nice to know. And just briefly, a comment about Newton's shell theorem. If we have a large sphere, then anything outside of it the force is the same if the sphere was just a point at its center. And conversely, if we have a spherical shell and you're anywhere inside the shell, the net force on you will be 0 if it's a uniform shell. And you can prove this with like complicated maths, but I won't do that now because we are very low in time. And gravitational potential energy is this just comes from integrating GMM over R squared dr. That's where the -1/r comes from. And so this is like a more accurate version of MGH. This is used if the distance is like really far away, I guess comparable to the radius of the Earth. And yeah, we have like 3 minutes. Let's do this question just for fun. This should be a pretty simple question. I'll give you like 45 seconds to do it. Okay, interesting. So let's end the poll here. Half of you chose D and half of you chose E. So actually the answer we were looking for here is E. And this is a common trick on the AP exam, so watch out for this. They say the altitude is 2 times the Earth's radius, but what that means is the altitude above the Earth's surface. So this distance is 2r, which means that this distance is 3r. So because it's proportional to 1/r squared, the force will be 1/9 of the normal mg force. Okay. Now I did have another question, but we don't have time, so let's skip it. Oscillations, these don't show up nearly as often. Well, they do show up, but they're not as many questions as some of the other sections. But basically what you need to know is if you have a restoring force, negative something times x, then that means that it'll oscillate with angular frequency omega is root k over m. And yeah, it'll be sinusoidal. So this equation here, some variation of this equation. And notice this omega doesn't depend on amplitude. So it doesn't depend on how far it was released or anything. And for pendulums, you can work this out with a force diagram if you want, but it turns out the net force will be mg sine theta. And then from there, you can work out what the angular frequency of a pendulum is. Also interesting, nice formula to know, t equals 2 pi over omega. This is just like, if you ever want to calculate the period, it's just the time to get a phase of 2 pi. So let's do one last example here. Actually, I did prepare 2 last examples, but we might not have time for that. All right, yeah, so a lot of people answered. I'll just end the poll here. Seems like everyone got it correct, so yeah, the acceleration's not constant. It's proportional to the force, which is proportional to the displacement. So I guess 1 and 2 are saying opposite things, so they can't both be true. That sort of rules out answer choice B and E. And yeah, the frequency is independent of the amplitude, as I just said. And one last question, this is a bit, it's a bit calculation intensive, but yeah. To do this, you can probably, it's easier to think in terms of the potential energy, which is 1/2 kx squared. So yeah, since x is 1/2, the potential energy is 1/4 of total energy, which means that the kinetic energy must be 3/4 of the total energy. Okay. And now that's the end of my lecture. So thanks to everyone for listening and see you next time.